Okay. Maybe I skip this and let me go on now to the first application, really. So this was all kind of theoretical stuff, and now we want to, as the first application, compute the equation of state, and that means essentially the thermodynamic quantities which we defined yesterday, so the derivatives of the partition function, which give you the pressure, the entropy, etc. So the bulk properties of our theory. So what Yuri explained yesterday was the simplified version which guides our intuition. So he was working with what we derived, namely the partition function for the free gases, okay, and which again we derived yesterday. So this is the two cases for fermions and bosons. They differ by these signs here, and of course that's the non-interacting limit. And then there are two interesting cases, the relativistic and the non-relativistic case. You know this from statistical mechanics. And yesterday you have already seen there is this factor t to the fourth pi squared over 90. That's the bosonic factor. The fermionic factor gets an extra 7 over 8. And the g in front here is basically counting the numbers of degrees of freedom of your free particle. So you have 1 unit of pi squared over 90 for every degree of freedom. So this is the relativistic limit. When your temperature is much larger than the mass, then your particles whiz about. And in the non-relativistic limit, when your mass is much larger than the temperature, then it's clear there is no kinetic energy. These things are sitting. Okay, and then you have this exponential suppression factor. So in other words, the pressure is always 0 or close to 0, and you have just energy, which is mostly due to the mass, to the rest mass of the system. This was also discussed yesterday in the hydrodynamics lecture. And then in the ideal gas situation here, in the relativistic ideal gas, you have that your energy is exactly 3 times the pressure, and in the non-relativistic limit, pressure is 0. Okay, so how does this play out now in QCD? QCD, of course, is not non-interacting, so it's not a free gas. We have interactions between the particles, and that's exactly where the difficulty is. So how do you compute this? And we discussed yesterday, if you do it in perturbation theory, then this stops at some order. So let's try to do this on the lattice. So what we want is to compute log z, say, that is giving us the free energy density divided by V, and all the other bulk thermodynamic properties follow. I listed them here again. We wrote this down yesterday. Now there is one complication on the lattice. You cannot compute the partition function directly because everything is normalized onto the partition function, so you would compute 1 basically. That's not very very useful. What you can calculate is expectation values of observables by your path integration, like we discussed in the last hour. And so what you do is a trick. It's called the integral method. So you take a derivative of log z with respect to, for example, temperature. Then you have temperature to the -3 times log z, and you derive that, or take a derivative with respect to temperature. This is giving you an observable which you can compute, and after that you integrate it again over temperature. So you undo the derivative, and then you get the free energy. Another technical complication in order to get this quantity. Okay, then you have to translate this to the lattice action, and maybe we'll skip that unless you want to do this yourself. It's not so terribly important. What I want to stress here is the bottom line on this slide again. This is again what we discussed earlier and what you remarked. So again, keep in mind, if I compute, for example, the pressure, okay, so this is log z with this integral method, it corresponds to the continuum expression, and then it has corrections of lattice spacing, and instead of A, I can always translate this to n tau. via the temperature. So the leading corrections to the pressure, for example, are 1 over n tau squared, which means a squared in this particular discretization. And then there are also higher order terms, and the question is, can I get this small enough so that the continuum pressure will be left over? And this was a long story. And here's a plot. This is quite old, but since this is a school, I think it's a very instructive plot, and it also tells you something about the sociology of science, which I'll explain in a minute. So this is a simulation from 2000 from the Bielefeld lattice group, and what you see here is the pressure as a function of, so this is dimensionless. Pressure has dimension 4. Okay, so you divide this by temperature to the 4th, and as a function of temperature expressed in MeV. And you see 4 different calculations corresponding to different particle content of your lattice theory. So the magenta curve down here is the pure gauge theory, no quarks. And then you add 2 degenerate flavors, light. You have 2 plus 1, so plus 1 means the strange quark is heavier than the U and the D, and this is 3 light quarks. So again, all 3 flavors are degenerate. And okay, and you see some structure. Let's first go for the structure. So what Yuri did yesterday was the simplified thing. So he was talking about nucleons and other hadronic particles and treating them like free particles. Okay, this is what you would do in the confined phase, because of this fact that you have exponential suppression with the mass. If we're talking about temperatures of about 200 MeV, like here or below, the only particles that are relativistic are pions. Okay, all the rest is sitting and it's not excited thermally. So if I say in first approximation I talk about pions in the confined phase and they are not interacting much, so I treat them like a free gas, I get my Stefan Boltzmann non-interacting pi squared over 90. Where did my factor of 2 go? Here it is. Oh, it's there is a G here, right? And the G is so I have 3 pions, okay, and they are 3 spin 0 particles, and so it's the energy and not the pressure. That's what I have an extra factor of 3. Okay, so this would be the expectation in a free gas of pions. Okay. On the other hand, if I go to, say, very large temperature and I invoke asymptotic freedom and say, okay, now let's suppose I have a free gas of quarks and gluons, then I simply count the number again of degrees of freedom, and I have to distinguish between bosons and fermions. But then I have gluons. I have 8 of them, right? Because my remember the A mu is A mu A TA, right? My A runs from 1 to 8, so I have 8 gluons. A massless gluon has 2 polarization states, so I have 16 degrees of freedom for the gluons. And then for the fermions, I also have 2 polarization states, spin up, spin down. Then it depends on the number of flavors I have. And I have 3 colors, and there is the 7 over 8 for the fermionic distribution function. So you simply count up your composition of your free gas and you get this number, okay? And you see, so simply on this reasoning, you expect between 0 temperature and large temperature, you expect a jump. Because your degrees of freedom, if you have deconfinement, then your degrees of freedom go up, okay? And you see a jump, okay, in the pressure. So the pressure goes up, and now comes the sociology part. This is quite amusing. So the arrows here give you the Stefan Boltzmann limit of a free gas. So if you had a free gas, you would end up, of quarks and gluons, you would end up at the position of the arrows. And what you can see is at a temperature of 600 MeV, we are quite far from the arrows. And so when this first came up, people were very happy and excited and say, you see, we this is the we have deconfinement. We're 80% there, right? We're almost there. 80% of this pressure is described by a free gas, so it's weakly coupled quark-gluon plasma. Then a few years later, or quite many years later, came the ADS CFT story, and people were saying, we clearly have the strongly interacting quark-gluon plasma because we're missing 20% of the contribution. That's to the, it must be strong coupling physics, right? So you see, it's the same curve, and it's explained by both weak coupling physics and strong coupling physics, depending on what you believe in. And as in real life, it's because it's neither black nor white. It's something in between, and you can understand this easily if you think about yesterday. We discussed we had 3 scales. We had pi t, we had g t, and we had g squared t. G, by the way, is not small, right? We're talking about a few hundred MeV. So you all should know what g is around there. It's close to 1, actually. Okay, so g and g squared gives you a factor that's not very different from 1. So the scale separation is not a separation. They are very close. Okay, and so the fact that you are 80% there comes simply has to do with the fact that this is governed by the Matsubara frequency. So this is the hard scale. So perturbation theory gives you about 80% correctly, and it screws up the rest of it for these quantities, and because it doesn't get these scales correctly. And now what the precise percentage is doesn't matter, but this is a quantity where perturbation theory has a decent chance, up to 25%. If you look at correlation functions of functions that are not dominated by these scales but by these scales, then perturbation theory is completely off the mark. Okay, and the whole thing is of course always a mixed bag of all 3 scales. So that's it's complicated, and if you do ADS CFT, then you pick up the lowest one, and if you do perturbation theory, you pick up the highest one, and the reality is a mix of all 3 of them. Okay, so so much for the background here, but now let's interpret these curves again. So this is very interesting because also if you say you count quarks and gluons, this is mathematically speaking a shady business, because quarks and gluons, they are not asymptotic particle states, right? Nobody has seen a quark or a gluon, even if you're discussing deconfinement. This is very important now. It's one of my points I like to make. Even if you are going to infinite temperature and your gauge coupling, suppose, is going to 0 or near 0, can you see a quark or a gluon? No, because if you do a gauge transformation, you transform it away. So the only things you can ever see, even at as high temperature as you like, is multi-quark or gluon states, because you need a color singlet. Okay, and you cannot have a color singlet from one quark or one gluon. So you can only see multi-particle states in any measurable device. So the interesting thing here is the pressure, of course, is a gauge invariant physical quantity, and it allows you to count numbers of degrees of freedom, but you see they are not like entire quarks or gluon. This is a very gradual thing, but you can clearly see that this goes up, the pressure goes up. And what's interesting here, this is where theoretical physics is cool, because you can tune the quark masses and add flavors. And now you can sit, for example, at a fixed temperature and walk through the curves, and you can clearly see that the pressure goes up as you add light degrees of freedom. So the interpretation, if I sit at one fixed temperature and I count the curves, I see my pressure goes up as I increase the number of light degrees of freedom. If I turn this argument now and read one curve from left to right, I have the same interpretation. So I'm entitled to interpret this as some sort of deconfinement. Okay, but what is released is a whole lot more complicated than individual quarks and gluons, because then we would be up at the arrows. So we do have remnant interaction between the quarks and the gluons, which accounts for this shortage of when we go away from the arrows. And as we increase t to infinity, of course, eventually we will asymptotically reach the arrows. But remember, the coupling runs logarithmically, right? So it's very slow. So you have to run for a long time until you reach the arrows. Okay. Of course, yes, yes. Yeah. This is not my plot, okay? The error bars here are essentially there's two kinds of errors. Very good point, thank you. So there's two kinds of errors. I mentioned to you the statistical error. This depends on the number of configurations that you have. So this gives you an error bar which is statistical, and then you have another error bar that comes from your finite lattice spacing. Okay, and this is much more difficult. This is systematic because you don't see it. The statistical you see in the fluctuation of your data, but the systematic error you don't see. You only see once you have done different lattice spacings, and then that gives you another error, a systematic one. So this is based on one particular lattice spacing. And so then maybe some of you remember there was something called by the way, you also see, of course, a transition of sorts, but you also see that it's smooth. Okay, there is no non-analyticity. All the curves are completely smooth, so it looks like there is no phase transition in this case. You smoothly go from the confined to the deconfined side. So now let's try to get rid of the errors, and this is by now achieved. Right. So we can interpret this as deconfinement, okay, even though we cannot see individual quarks. So this is now a few years down the road, 2010, and by now it's even better. So here is now the systematic error as well. So here is the width here is the statistical error, okay, for one type of simulation, and 1 NT means one number of time slices. And remember, so T was 1 over A times NT. Right? And if I keep my physical temperature fixed in physical units, then changing NT means I change A. Okay, so larger NT means smaller lattice spacing. So what you see here is 3 different lattice spacings, and now you can see that this is statistical error, and you can see from the fact that the 3 curves lie on top of each other, you can see that the systematics is under control as well. And you can also see here, so this here is the interaction measure, which I should write down, but I always get the order wrong. So this I is E minus 3p, which is 0 in an ideal gas, because in a non-interacting gas, right, the pressure is, the energy is 3 times the pressure, or the other way around. I always confuse them. So that's why people say this is the interaction measure. Okay, and what you see here is for very low temperature, this is very small. That's why you can approximate things with non-interacting pions. And for high temperature, it becomes asymptotically, again, very small. That's when you can describe things by a gas of quarks and gluons. And everywhere in between where this is significantly non-zero, that's because you have interactions. Okay, and you see that this is strongest around the phase transition. And again, this is the motivation for this as a strongly coupled quark-gluon plasma, because here you have a strong remaining interactions. Okay, and in the meantime, so these things sit on top of each other, but you can actually extrapolate this to 0 lattice spacing. This has been done by now for the case of physical quark masses, and this is only a few years old, so this was not possible for a long time. Okay, so this is the equation of state. By now people have moved to the next step, and they include the charm quark as well. And now we want to move on to the next couple of subjects, and I guess we can certainly do 1 or 2 more subjects here. The next subject is screening masses. That's another observable which tells us something about the dynamics of the quark-gluon plasma. So what is a screening mass? Let's start with example QED. So you're all familiar with the Debye screening length. So the picture is you have, say, a static charge, a heavy charge, immersed in a plasma, and then the plasma polarizes, so the charge is rearrange themselves around the static charge. And if you go further away from the source, then you see a screened field because the polarization field supersedes the field of the static charge. So you have screening, which means your photon becomes effectively massive. And there is a screening length which is defined by the correlator. So you take the correlator in electrodynamics of electric fields, okay, separated by, and this is now the important thing, by a spatial distance. So you go away in a space direction. And then you have an exponential decay of your field strength, and the coefficient in the exponent is the Debye mass, or the inverse screening length. And if you Fourier transform this, then you basically get the Coulomb potential turned into a Yukawa type potential with the Debye mass as the screening mass. So this is the concept in QED, and now people tried to translate this to QCD and to take the appearance of screening as a signal for deconfinement, which is also employed in heavy ion collisions. So the idea was that if you take a static source, that's something that's heavy, so a heavy quarkonium, for example, should be suppressed in the deconfined phase clearly as a bound state, and that was supposed to be a signal for deconfinement. And now, unfortunately, we have a complication compared to QED from the fact that we are dealing with a non-abelian gauge theory. Clearly, gauge invariance in QED is expressed in the fact that you can gauge transform your gauge potential A, and you don't change the fields. So the electric and magnetic fields are the same. So E and B are the same if you do a gauge transformation. And this is not true in a non-abelian field theory. The field strength tensor also transforms, so E is not gauge invariant. And that is one caveat when you look at this definition of screening. So if you go in the same way and ignore this problem for a moment, then you have a Debye mass, that's what we discussed yesterday. That's the screening mass of the electric, so the color electric gauge fields, and it's living on the scale GT. We discussed this yesterday. So that's the leading order result. But then you have a correction that goes logarithmically, and you have a correction that goes with the G square T scale, which is the magnetic one. And again, this coefficient here is already completely non-perturbative. Okay, so this receives contributions from all orders in perturbation theory. So it is related to this Linde problem and cannot be calculated in perturbation theory. So can we do this a bit better? And the answer is, of course, we can. So we can do this to something that's amenable to the lattice, and in principle also to a measurement. That would be nice. I'm not sure if this is ever feasible experimentally. But so what you do is you look again at spatial correlation functions, and to make this physical, you take a gauge invariant operator that you separate, and then you measure its exponential fall off. So the general definition is simply like in QED, you take something physical, insert it in the plasma, and then you measure its exponential decay in a spatial direction. That's a screening mass or an inverse screening length. And then you can classify these with quantum numbers of the source here, which you correlate over a spatial distance. And so what you do is this works exactly like a spectrum calculation in QCD, except that the normal spectrum calculations are correlation functions in time, because that gives you the eigenvalue of the Hamiltonian, right? And here it's the eigenvalue of a Hamiltonian that acts in the space direction. This is what we discussed in the connection with the transfer matrix. You can also have it move in a Euclidean space direction. And so then you have quantum numbers that characterize your system. And because now we have finite temperature, one of our directions on the lattice is short. And so you have JPC, like in ordinary spectrum calculations, and you have an additional quantum number R. And the JPC is now restricted to SO2 rotations. So our spatial Hamiltonian is HZ. Okay, so this is is basically propagation in the z direction. And that acts on a wave function which live in x, y, and tau space. And the tau space, this is the time direction, this is short because of our relation between Euclidean time and temperature. So x and y are infinite, tau is short, so I have basically only rotations in xy direction, and I have reflection in the tau direction, which is the short one. And that explains this particular kind of quantum numbers. Okay, once I have defined this, I have a completely well-defined problem. So I take a gauge invariant operator A and correlate it over space, and its exponential decay will give me a screening mass. And these screening masses and their symmetry behavior teach you something about what's going on in the plasma. So here are again two rather oldish calculations. One is in pure gauge theory, so there are no quarks, and then the spectrum is one of glue balls, right? In the confined phase you would have glue balls, and in the deconfined phase you would have gluons or conglomerates of gluons. And the gauge invariant states, gluons are not observable, the gauge invariant states would carry glue ball quantum numbers. And so these are denoted here by, so the ground state would be a spin 0, parity, charge conjugation plus, and reflection is also plus. So this is the ground state here. And what you can see is if you come from the left, so from low temperature, this is almost at the same value of the glue ball mass in the vacuum. So it doesn't move very much as a function of temperature until you hit the deconfinement transition. And in pure gauge theory, this is a real transition. And here you see this, the curve is not smooth. You have a dip, and then this thing comes up again. And then you asymptote to some constant value if you plot m over t. And again, you can understand this because with our mass scales, so this glue ball now depends on the quantum numbers, but if you it goes either like gt or g squared t, so it's proportional to t. So if I take m over t, okay, eventually this will be flat. So you can see again at high temperature you recover the perturbative intuition, and in between it's much more complicated than that. Here is now dynamical simulation. So this includes quarks, and you can, for example, look at mesonic correlation functions. And again, you have here temperature, and this is now m in units of R0, which is a constant, so this is not divided by m. And again, you can see at high temperature this goes linearly, this rises with temperature. And remember, these mesons involve quarks, and quarks have Matsubara's frequencies 2n+1 times pi t. So this is always non-zero. And you can precisely see the t again. This is going like t. And you can see here is different, these are different mesons, so they have different quantum numbers which are related by chiral symmetry rotations. So remember, chiral symmetry is a rotation in flavor space. Okay, if I have 3 flavors, then you rotate in the U, D, and S space. And you see at low temperature, these mesons are very different. And if you go to high temperature, then they start to become all degenerate. And this is a signal for the restoration of chiral symmetry, so the flavors become indistinguishable. Okay, so you can nicely see how this is realized, and as you compare temperatures below and above the critical temperature for deconfinement. Okay, then one can do a few more things about the plasma and see when is certain intuition, when does it apply or does it not apply? So this is an analysis from my time as a postdoc. I was in that collaboration, and we studied a system of scalar QCD, because scalars are easier to simulate than fermions. And the idea was, can we learn something about these different scales here? So in scalar QCD, we don't have this one. This is missing, and we just have these ones. And now you can, so these are screening masses in various quantum number channels, which involve glue balls, as in the three-dimensional Yang-Mills theory. So the black symbols here, they live on the scale g squared t. And the white symbols, they live on g times t because they involve a zeros, which go like the Debye mass perturbatively. So if you have this scale hierarchy, okay, then you would say, so if you have a bound state of two of these guys, you would expect, say, two propagators or three or whatever, but they are all proportional to gt. And if I have a bound state of these guys, I expect it should go by g squared t. And if I have this scale hierarchy, then these guys should be lighter than these ones. And what you see at twice the critical temperature of the phase transition, you see that the lightest state by far is one of these color electric ones, which is this one. But that should be the heavier one. Okay, and that just tells you that, but that now I'm already at double the deconfinement temperature. Okay, I still have in this soft sector, so I don't have the hard sector here, but in these scales they're completely non-perturbative. Okay, your perturbative intuition will not get you anywhere. And then you can study when do these scales cross, and because the coupling is running logarithmically slow, you can see you have to go to ungodly high temperatures, and now you see that the hierarchy is reversed. Now the lightest state is a black one, so that's the g squared t one. But the crossing takes place at about 10 to the 4 or so Tc. So here we looked at the crossing, and you see this happens very late. Okay, so the soft modes in the plasma are indeed strongly coupled, and the hard modes are weakly coupled, and they're all talking to each other. So it's a very complicated business. Okay, and again, this screening mass business is a method to study chiral symmetry restoration, and you can then study details when you look at how the different states, like the sigma and the pions and the eta prime and the deltas, how they are related by chiral symmetry transformations, either in the SU2 sector or in the axial U1 sector. And so you can compare the screening masses of these states to learn something about the symmetry. Also very interesting studies. Okay, let me move on to one more thing about confinement. Namely the study of the free energy of a static quark-antiquark pair. We discussed that earlier. So this measures you, so this is a hypothetical system with infinitely heavy quarks. And you can do an analysis with this transfer matrix and find that this thing has an exponential decay. So this is a correlation function of Polyakov loops, and it corresponds to a system with free energy with two static quarks present or not present, and the free energy difference tells you something about the confining property. Let me again skip the mathematical details here and simply say that I can evaluate this again with a complete set of eigenstates of the Hamiltonian, and then you have again your Boltzmann weighted sum, okay, with the energy eigenlevels, and the Boltzmann weight is simply given by the temperature relative to the energy levels of these states. And the energy levels of these states are precisely the static potential. So you have a heavy quark, heavy antiquark, and that's precisely the static potential that gives you the confining properties. And the leading term is what we call V, so that's the potential from the Wilson loop. And if you do this in a thermal situation, then that's what we discussed also yesterday. You have this superposition with the Boltzmann weight. Okay, so in other words, there is a potential, but there are also excited states, and then the thermal excitation populates all of them depending on how much temperature you have. Let's see what this looks like. So here is again data. So this is now quenched limit, so only gluons and these two quarks, quark and antiquark, at a separation. And so this thing here is wrong labeling. This should be an F really, that's the free energy, so it's all thermal excitations on top. But what you can see, so these are different, this is R, separation of the two sources, and these different lattice gauge couplings, beta, they tune the temperature, right? That's what we discussed at a fixed and tau. They tune temperature. So what you can see is you have a linearly rising free energy, which is a thermal sum of all potential excitations. So they all go linear with distance, which is the signal for confinement. And as you increase temperature, you see that your slope gets flatter and flatter and flatter. And once you are above the critical temperature, you see you have a Yukawa potential, and the free energy also is screened. So you have essentially screened your color force by some mass scale. And now you can ask, what is this mass scale that screens this? A Polyakov loop is a gauge invariant object. So you have a correlation function of two gauge invariant objects. So what you exchange between must also be gauge invariant. And you can see that the screening mass of this thing here, so here is the screening mass as a function of temperature. So here you have something flat. And the value of this screening mass is precisely consistent with the lightest glue ball that I have shown you earlier. So this is precisely the lightest screening mass in this pure gauge calculation. It's this guy. Okay, so this fits. This is what screens the Polyakov loops in the plasma. Okay, and then again, you can add dynamical quarks, and if you add dynamical quarks, then you all know what happens. Then if you have a linearly rising potential, you separate your static sources. At some point, you have enough energy stored in the string in the flux tube between your sources, and you can pop up a quark-antiquark pair of the light type, and then you screen the potential also because you get two heavy light mesons. Okay, and that's what you see here. So here is the linear, the pure gauge kind of free energy at finite temperature, and if you have static quarks, you see this will break off at some distance, and as you increase the temperature, this break-off distance will become earlier and earlier. So you see that the color force gets screened by dynamical fermions in this case, also of course at finite T, and the temperature helps this screening process. So all our qualitative understanding of QCD can be nicely checked in these simulations. Okay. And maybe a last remark on this subject. So sometimes people are interested in certain color configurations of quarks. And that goes a lot into phenomenology, and there are a few inaccuracies that are sometimes wrong. So this is still around sometimes. I hear this still in talks. So people are talking about the free quark-antiquark energy, which is what we just discussed now, and then they talk about a singlet channel and an adjoint channel, and that depends on how you take the trace. So here you take the trace of the Polyakov loop before, and then you correlate it, and each of them is gauge invariant. So this is a well-defined. The first line is a well-defined observable. The second line is not. Here you first take the product of the loops and then only one trace. This thing is gauge invariant. It's not gauge invariant. So this you can only calculate if you fix a gauge on the lattice. Same thing is true for this F8. This would be now what people call the octet channel. So you have 3 and a 3 bar, and they can be either in a singlet configuration or in an octet configuration. And this is the difference between these two things, but they only exist when you So you can only measure them if you fix a gauge, otherwise you get 0 in a simulation. So now people wanted to get the Debye mass. That's the motivation for this thing. I told you this thing decays with the screening mass here is of the glue ball type, so it's a singlet thing. And people wanted to get what is the mass, the analog of the Debye mass in QED. That would be the mass of an A0, okay? It's problematic because A0 is not a well-defined gauge invariant object in this case. Okay, and what you can do is, again, you can do an analytic spectrum analysis. You don't even need to compute the numerics of this, and you can see that all of these three channels, okay, they all decay with the same eigenvalues En of the gauge invariant Hamiltonian. So the spectral information is the same because that's gauge invariant, and the only difference is in the matrix element before, which is a gauge variant, not well-defined object. So this is gauge invariant, but these things are gauge variant. But the spectral information is the same in all three channels. So this distinction between the F8 and the F1 doesn't make much sense, and it depends on the gauge. This is just a comment if you see this or read this somewhere, to be careful. Okay, and that's where I stopped today. I made up all my time that I lost yesterday, so we're back on track. Thank you. Yes, I maybe I give them to you to put them online. So I have a collection of 3 or 4 exercises. If you feel like doing them or discussing them, I'm around. It's voluntary, I understand. But there's a number of things to think about these concepts that we talked about. Yeah. Any more questions?